Electricity is usually treated like something that comes from a switch on the wall. You flip it on, and it's there. No questions asked. But that assumption hides a much deeper system underneath everything most people use every day. Because at some point, that electricity had to come from somewhere. And that's where the question becomes more complicated than it first appears. Can plant material really produce electricity? At first, the idea sounds almost too simple to take seriously. Plants grow, plants die, and somehow that becomes power for homes, devices, or entire systems. It feels like a shortcut to something that normally requires large infrastructure and constant input. But the more you look into it, the less it looks like a shortcut and the more it looks like a process that most people misunderstand from the beginning. The first assumption people usually make is that plant material behaves like fuel in the traditional sense. Something you can take, process, and directly convert into electricity in a clean and immediate way. But plant material doesn't work like gasoline or batteries. It behaves like stored biological energy that needs to go through several steps before it becomes usable in any electrical form. And those steps matter more than the material itself. When people first explore this idea, they usually imagine a simple transformation. Leaves, grass, or wood go into a system, and electricity comes out the other side. Straightforward input, straightforward output. But in reality, nothing in that chain is straightforward. Because plant material is not uniform. It varies in moisture, density, composition, and energy content. Even the same type of material can behave differently depending on how and where it was grown. That variability creates the first major challenge. The second challenge is conversion. Plant material doesn't naturally produce electricity in a usable form. It has to be broken down, processed, or transformed through intermediate steps before any electrical energy can be extracted. In most real-world systems, that means biological decomposition, thermal processing, or gas production stages come first. Electricity is often the final step in a much longer chain. And that chain introduces time, control, and efficiency issues that are easy to underestimate. Because once you introduce biological or thermal processes, you are no longer dealing with a simple, on-demand energy source. You're dealing with a system that depends on conditions like temperature, moisture levels, oxygen availability, and material consistency. And if those conditions shift, the output shifts with them. That's where expectations and reality begin to diverge. Many people assume that if plant material contains energy, then scaling it up should simply increase output. More material, more power. But energy systems don't scale that cleanly when biological processes are involved. Instead, scaling introduces new constraints: storage, decomposition rate, system stability, and maintenance requirements all become more important than the raw material itself. So even though the idea of plant-based electricity feels intuitive, the actual implementation becomes a systems problem rather than a materials problem. And that shift changes how you interpret the entire concept. At this point, it's helpful to separate what is visible from what is not. The visible part is the plant material itself: grass, wood, agricultural waste, organic matter. The invisible part is everything required to turn that material into usable electricity. The containment systems, the conversion mechanisms, the environmental conditions that keep the process stable, the time required for breakdown, and the energy lost at each stage of conversion. Most misunderstandings come from focusing only on the visible part. But the hidden structure is where most of the complexity lives. And once you start seeing that structure, the question changes. It's no longer just about whether plant material can produce electricity. It becomes about what kind of system is required to make that possible in a consistent and meaningful way. That's where a key turning point usually happens in understanding this topic. The real issue isn't whether plant material contains energy. It does. The real issue is how difficult it is to control the transformation process in a way that produces stable, usable electricity. Once you see it that way, the conversation shifts away from the idea of a simple alternative energy source and towards something more grounded: system design. Because at that level, plant material is just one input among many. What matters more is how the system handles variability, how it manages conditions, and how efficiently it converts one form of energy into another. And that's where most real-world implementations differ significantly from the simplified version people imagine at first. Some approaches focus on breaking material down biologically to release gases that can later be converted into energy. Others focus on thermal methods that extract heat energy directly. Each method has its own constraints, trade-offs, and requirements. None of them are inherently simple, but none of them are inherently impossible either. They just operate under different rules than most people expect when they first hear the idea. And that expectation gap is usually what leads to confusion. Because when people hear, plant material produces electricity, they often interpret it as a direct and immediate process. But what actually exists is a layered chain of transformations that depends heavily on design, control, and environmental stability. Once that is understood, the idea becomes less about discovery and more about engineering. And engineering always comes down to constraints: materials, time, efficiency, and control. Plant material fits into that framework, but it doesn't bypass it. So instead of thinking about it as a simple answer to energy needs, it becomes more accurate to think of it as a component in a larger system that still has to obey the same physical and biological rules as everything else. And that's where clarity starts to form. Not in the idea that plant material is a hidden solution waiting to be unlocked, but in the understanding that energy systems are always about trade-offs between simplicity, efficiency, and control. Once you understand that balance, the question itself becomes more precise. Not, can plant material produce electricity, but, under what conditions can plant material be part of a reliable energy system? And that shift in framing is usually where the misunderstanding finally clears. Because it brings the conversation back to something practical, measurable, and grounded in how real systems actually work. If you want to go deeper into how these systems are structured and how different conversion methods compare in practice, there's a structured breakdown available in the description. You can also find a step-by-step framework that explains how these processes are typically approached in real-world applications. And the goal isn't to push a conclusion. It's to understand what is actually required for any of this to work in the first place. Because once you understand the structure, the idea becomes a lot easier to evaluate.